Good morning. Today we're going to be graphing polynomials. I'm going to give you some criteria, and then based off of what I give you, you will draw a polynomial based off of what I give you. A few things that you need to make sure you've done. You need to make sure that you've caught up to today, that you've done your end behavior, that you have taken a look at graphs, the different shapes of the graphs, that you know about even and odd degree polynomials, and that you know how you can tell by looking at a graph what the real zeros are. Hopefully, also, I want you to pull out your notes on this day from a couple of days ago when we talked about end behavior and when we talked about the different shapes and turning points of graphs. So before you get into this video, you really need to make sure that you are up to speed with what we're doing, because we're going to be doing a lot of concept work, but you got to make sure that you understand the concepts that I'm talking about in this video. So let's get started. So I'm going to go through 6 different graphs, and then at the end of the graphs, we will talk about some different patterns and things that we should recognize based off of the graphs that we have graphed. So here's the first one that we're going to take a look at. So we're going to draw a cubic function with one real zero. So in order to achieve this, I need to know what a few words in here means. So cubic is the number 3. So if something is cubic, it either has to go up, down, up, or it has to go down, up, down. So cubic, I need to keep that in mind. One real zero means it only should cross the x-axis in one spot. So when I come over here, there's going to be a whole lot of different options that I can do. Many different options that I can do, as long as it's cubic and it's one real zero. So no particular reason, I'm going to graph one that looks like this. Okay. This is not the only one that's possible. This is just the first one that came to my mind. It's cubic because it goes 1, 2, 3, and it crosses the x-axis in one spot. So that's one real zero. So we're going to label this. Our degree for this is cubic, and I had one real zero. So real 1. And my pencil broke. Okay. Here we go. So my degree is 3, and there's one real zero. I got that right off of the information that I'm giving here. A cubic function, one real zero. Okay, let's try another one. Okay, number 2. Number 2 wants us to create a quintic function with 3 real roots and 2 imaginary roots. So create a quintic function with 3 real roots and 2 imaginary roots. Quintic is the number 5. So my options are up, down, up, down, up. Or down, up, down, up, down. So just a general shape for what quintic functions look like. They have to follow one of those trends. It has 3 real roots and 2 imaginary. So it only can cross the x-axis 3 times. So here's my x-axis here, and it only can touch in 3 spots. So let's see, one possibility that I can do, and there's infinitely many possibilities out there, as long as the shape is quintic and it has 3 real roots. So it crosses the x-axis 3 times. So I'm going to draw mine. This is 1, 2, 3, 4, 5. Okay, so let's make sure this follows the criteria that I'm giving. Is it quintic? So 1, 2, 3, 4, 5. So yes, it's quintic. So check there. Are there 3 real roots? It crosses 1, 2, 3 times. So there are 3 real roots, and the imaginary roots are going to come up in just a minute. So I'll talk about that in a little bit. But my degree is 5, and I have 3 real roots. So we're in business. So that is number 2. Next, let's see what it tells us to do. This time we're going to create, and I'll put it over here. We're going to create a cubic function such that as x approaches positive infinity, my function approaches positive infinity. So cubic means 3. We've already taken a look at that. Number 1 is a cubic function because it goes 1, 2, 3, so that's a cubic function. This time I need to check and make sure my end behavior is what the problem is telling us to do. So as x approaches positive infinity, that's on the right-hand side of my graph. So this side where my colored pencil is, the right-hand side of my graph. So as x approaches infinity, my function needs to be going up. So I need to make sure my end behavior over here is going up. So if I'm doing a cubic function, that means my only option is 1, 2, 3. So 1, 2, 3. Now, you absolutely could have drew in a cubic function that only crossed the x-axis once. This one crosses 3 times. So this one, our problem here didn't specify if it wanted 1 real root or 3 real roots. It actually didn't say anything about the roots. The only thing we had to follow was that as x approaches positive infinity, that's on the right-hand side of my graph, my function had to be going up. So if I can compare that to number one does not have the appropriate end behavior that we needed. The end behavior said on the right-hand side, my function should be going up, and this one's going down. So number 1 would not work for number 3. So again, number 3 says as x approaches infinity, my function approaches infinity. So it had to be going up on the right-hand side. So if we label, my degree is 3 because it's cubic. 1, 2, 3. And for this particular graph, I have 3 real roots. And 1, 2, 3. And I'll go back and label that for the other ones. 1, 2, 3. And this one had 1. All right, so we're halfway done. Again, I'm giving you different characteristics, and you have to graph it and state what you notice. All right, let's move down to the bottom here. So we'll do 4 through 6 down here. Okay. These are the directions for number 4. Create a 6-degree function with 2 real and 4 imaginary solutions. Now, the imaginary part is going to come up in just a minute. When we start looking at the patterns, you'll start to see where that comes into play. But a 6-degree function, so it has to have 6 like curves and things like that. And it only can cross the x-axis twice because it says 2 real roots. So it only can cross twice. So lots of different possibilities. I can go 1, 2, 3, 4, 5, 6. So that would be a possibility. Okay, let's double check. It's got to be a 6-degree polynomial. So let's count. So this is 1 to that turning point, 2, 3, 4, 5, 6. So it's a 6-degree polynomial. It only can cross the x-axis twice because it says 2 real solutions. So if I check here, once, twice. So that means we have followed the criteria of this problem. So let's label. The degree is 6, and it said 2 real roots. All right, so that's it for that one. Next, create a quadratic function with no real zeros and end behavior as x approaches infinity and x approaches negative infinity. My function approaches negative infinity. So let's go through that because there's a lot to unpack in there. It's got to be quadratic. It cannot cross the x-axis, and the end behavior on both sides, on the right and the left side, my end behavior on both sides should be negative infinity. So if it doesn't cross the x-axis, I can't draw it up here, somewhere up here, because the arrows of a parabola are going to go down and cross the x-axis. So I cannot draw it up here. So I have to draw it down here somewhere, and I have to make sure my end behavior on both sides is negative. So again, lots of different possibilities. This is just one of them. Okay. So it does not cross the x-axis. It's going down because the end behavior on the right and the left side, the end behavior had to be going down. So this is just one possibility. If you wanted to draw it all over here in the 4th quadrant, if you wanted to draw it all over here in the 3rd quadrant, we just had to make sure it was going down. So our degree, quadratic function is 2. And no real zeros. So my real solutions, there are no real solutions, no real zeros. And last but not least, and then we can do some compare and contrast and go back and talk about our imaginary solutions. Number 6, Says create a quadratic function with a double root at 3. So it's got to be quadratic. So it's going to have a similar shape to number 5. We just got to figure out what this double root at 3 means. So a double root means it's going to touch, and I'm going to put it in quotations, it's going to touch the x-axis twice. So it has a multiplicity of 2, and we'll get into multiplicity probably in the next video, the next day. So a double root at 3. So that means it's got to cross the x-axis at 3. So it's actually going to turn out to look like this. So this spot here is, we're going to call it a double root. It's kind of like it's touching it twice. So when you're doing the even functions, they either got to both go up or both go down. And your only options with these, as far as your real zeros, is going to be 0 or 2. So there's no other way to draw this without coming down, touching it, and then bouncing back up. So it doesn't go through, like if I look at number 4, it doesn't go through the x-axis right here. It comes down, it touches, and then it bounces back up. So that's called multiplicity. And we'll be talking about that in the coming days. So this is a double root at 3. So this is 1, 2, 3, and I have a double root at 3 right here. So my degree for this quadratic is 2. This is a parabola. And I got a double root, so that means I got to count it twice. It's got a multiplicity of 2. So now that we've gone through, let's see if I can get all of them in here at the same time. Let's talk about some things that we should notice. So we've labeled the degree for everything, and we've labeled the real for everything. Something you should know is that your real roots plus your imaginary roots must equal your degree. Again, the real roots plus the imaginary roots must equal your degree. So we're going to go through all 6 of these and label the imaginary roots. Okay, so we're going to go through each of these and label the imaginary roots for each one. So make sure as you write your notes that you write down somewhere that your real plus imaginary has to equal the degree. Again, one more time, real plus imaginary has to equal the degree. So for the first one, real plus imaginary has to equal the degree. If the degree is 3, I can just subtract to find my imaginary. So 3 minus 1, that leaves space for 2 imaginary. So it leaves space for 2 imaginary. 1 plus 2 gives me 3. Next, I need space here. I've already taken care of 3, so 3 plus something is going to give me 5. If you just subtract, it'll give you your imaginary solutions. I got 2. This one is a degree of 3. I've already used all 3, so this leaves space for no imaginary solution. So I have 0 imaginary solutions here, and number 1 and number 2 both have 2 imaginary solutions. Let's jump down to the bottom row, number 4. 2 plus something gives me 6. So you can just subtract. This leaves space for 4 imaginary solutions. I have a degree of 2. My real is 0. So 0 plus something is going to give me my degree. That something that I'm missing is 2. And with number 6, my degree is 2. I've already used everything I have. So this leaves space for no. So again, your take-home point here is that if you take your real solutions, add them to your imaginary solutions, it'll give you your degree. Take the real, add it to the imaginary, it'll give you the degree. So make sure you write that down, bold it, highlight it, something along those lines. So when we were going along and I was telling you about the imaginary solutions, like for number 4, if I bring that back up, I told you to do a 6-degree function with 2 real and 4 imaginary. The imaginary will not appear graphically. So once we took care of the 2 real solutions, we automatically were going to get into the imaginary solutions if we did everything correctly. So that's one thing that I want to notice. I want you to notice. A couple other things I want to notice. I did color code it on purpose. So if you look at the green and then look at the red, the green functions are a specific type of function, and then the red functions are a specific type of functions. So if I look at 1 through 3, what type of function is all three of these. Okay? Hopefully, you said that all three of these are an odd degree function. So I'm going to write that somewhere. 1 through 3 are odd degree functions. So cubic, quintic, cubic. Those are odd numbers. 4 through 6, you should notice these are all even degree functions. So 4 through 6 are even degree functions. So make sure you write that somewhere. I'm also going to write somewhere that real plus imaginary equals our degree. And I'm going to put that in a little bubble. So real solutions plus imaginary equals our degree. 1 through 3 are odd degree functions. 4 through 6 are even degree functions. So you can look at their numbers there. We got a couple of 2s and a 6. Those are even numbers. Let's see what else we notice. If you look at your end behavior for an odd function, 1 is up, 1 is down. 1 is up, 1 is down. 1 is up, 1 is down. So for all odd degree functions, your end behavior, 1's going to be up and 1's going to be down. If I compare that to an even degree function, they're either both going to be up or both going to be down. Notice number 4, they're both down. My end behavior is down. Number 5, notice my end behavior, they're both going down. And number 6, notice the end behavior is both going up. So for an odd degree function, your end behaviors will be different. For an even degree function, your end behaviors will be the same. And the last thing, because this has lots of different conceptual things and patterns that hopefully you notice. If you look at your imaginary solutions, 2, 2, 0, 4, 2, 0. These are all what type of number? Hopefully you said that they're all even numbers. You will never have an odd amount of imaginary solutions. So again, you will never have an odd amount of imaginary solutions. So imaginary solutions, and I am abbreviating here, imaginary solutions come in pairs. So imaginary solutions come in pairs, meaning you won't have 3 of them. You won't have 5 of them. There'll never be 7 of them. They like to buddy up. It'll be an even number. So 2, 4, 6, 8, 10, 0. So imaginary numbers come in pairs. You should never, ever have an odd amount of imaginary solutions. So make sure you keep this handy. It's going to help you for the next few days, and it'll help you when you're graphing your polynomial functions.